thank you all for coming for another Our Universe Revealed. Familiar faces in the audience, back again and some new faces. So thank you all for coming. This evening, I'm going to talk a little about science, but I'm also going to get out my crystal ball and tell you what you might be hearing in the exciting science news in the next 10 years. We'll stick with science news. It'll be happy science news. And you might think when we have all of the astronomy speakers or general physics speakers up here telling us how much we know about the universe, we know a huge amount what's going on. And we know a lot, but there are still many, many questions out there, big questions we still don't know the answers to. And I'm going to talk a little bit about that, put it in context, and some of the tools and things that we're going to be seeing, as I say, over the next 10 years or so. So this picture, you're probably all very familiar with recently if you've been watching the news, the James Webb Space Telescope. We'll talk about that in a little bit, but that's a future telescope, future discoveries coming our way. I want to pause and look back a little bit for the last 10 years, because I think it's quite, we lose the perspective of how fast science is advancing at the moment. And I want to put that in context of some of the recent discoveries we've made, talking more about what's coming next. How do scientists, and particularly astronomers in this context, decide what we should study? How do we decide where to spend money from the federal government on research? And then I'm going to really look further ahead, not just the next decade, but what is going to be coming beyond 2032. So recent discoveries. Let's start there. This is an image from 2005 from the Hubble Space Telescope. And I'm going to ask you a simple question that might put it in context. When you went to school, how many planets did we have in our solar system? 9. So what you're looking at here is the best knowledge we had of Pluto back in 2005, the furthest out planet, we'll say, in our solar system. This is Pluto here, its moon Charon, and then its 2 other moons, Hydra and Nix, were actually discovered in 2005, and this image confirmed them. So keep in mind, this is 2005. In 2006, NASA launched a mission called New Horizons that went out to study the outer parts of the solar system. So when it was being designed, Pluto was a planet. We launched it January 2006. It took 9 years to get to the outer parts of our solar system. Swinging back to 2005, a team of astronomers at the Palomar Observatory in California discovered Eris, which is another object about 3 times further out than Pluto from our sun and more massive than Pluto. And what happened is we went, well, that doesn't really seem like a planet. But if it's not a planet, how can Pluto be a planet? So this is a sort of a scale model. This is Eris on the right. It's bigger than Pluto. So in 2006, August 2006, mere 8 months after New Horizons had launched, Pluto was no longer a planet. So New Horizons was still on its way to study Pluto, but it was now going to study a dwarf planet. It wouldn't get there until 9 years later in 2015. That's how long it takes to go across our solar system. So we had that image I started with. That was all we knew of Pluto. New Horizons was designed not to land on Pluto, to fly past it and continue out through the solar system. So it got there 14th of July, 2015, and this is what it saw. We had no idea what we were going to see. It looks like perhaps you could imagine this being one of the rocky planets, like we have in it to the solar system. That's sort of what it looks like from the outside. What actually we think this is the surface of this is solid water ice, but it's so cold, it acts like rock that we'd see on Earth. You have these brighter regions, these darker regions, all kind of things. And to give you a sense of this scale, this is sort of the broad view of the planet, and they actually reprocessed and released this back in 2020 with a high resolution version. I'm just going to zoom in on this region here and zoom in even further. So what you're seeing in this image is huge chunks of water ice like we have on Earth, but super cold. So it's incredibly hard like rock. These blocks are up to 1.5 miles high, all crammed together, making what we look like are mountains. It's what it looks like. Between those, you sort of have this other material that's slotted in. And we think that that's potentially blocks of ice and things cramming together. And then we've got this other material down at the bottom. Laszlo. It is our best understanding, and in terms of the chemical composition we have from that, that is our best understanding. But again, it's a fleeting glimpse as we go past Pluto. We're not going down to the surface of and measuring. So it's like trying to look at the universe as we do as astronomers from a distance, not going to the surface, not like in a lab measuring. So it's our best theory, our best understanding of what we have right now. Now, why we have this gap here, we still don't really understand, but what we can tell from the chemical composition is this is water ice, and this is actually different types of ice, sort of nitrogen-based ices, things like that. And that becomes, it's just different in terms of its properties. And that's why we get these flat, smooth regions with these hard, solid water ice areas. We had no idea we were going to see this back in 2015 when we launched New Horizons in 2006. But it tells us a huge amount about the outer part of our solar system. One of my favorite images from New Horizons was not actually staring at the planet itself. If you imagine we have the sun at the center, we launch the spacecraft from Earth, it travels out past Pluto, and it keeps going, and it turns around and it looks back. What it saw was this blue haze around the surface of Pluto. And if you look carefully, you can sort of even see sort of mountains and features on the surface here. This blue haze is what was described as a photochemical smog. It's basically methane gas that we're illuminating the sun through and we're scattering the light. And that's why it's blue. It's kind of why our own sky is blue. So we have this blue atmosphere of methane around Pluto. Again, we didn't know what we were going to see, but we saw some stunning images from the outer parts of our solar system. We kept going though. We didn't stop in 2015. New Horizons was designed to study right out at the edges of the solar system, what's called the Kuiper Belt. And on the 1st of January, 2019, we flew past this object called Orakhoff. Again, we know these objects exist in the outer part of the solar system. They're just tiny specks of light that move in the sky. We had no idea what they look like. It's two lumps of rock glued together. We've also looked at comets recently, and they sort of have this two-body shape as well. So we're building up more idea of the components in our own solar system. From one mission that was launched to go to a planet and went past a dwarf planet instead. So incredible in terms of the science we did with the mission, based on that one image from Hubble. We've done lots of other things as well in our own solar system. In January 2004, we launched the Rosetta and Philae missions. Rosetta was designed to orbit around the comet Churyumov-Gerasimenko, or 67P as we call it as astronomers, because it's a little less of a mouthful. And it had a lander that went down to the surface. So just like Laszlo asked, well, how do we know? Is it water ice or not? This was, we are going to the surface and we're going to directly measure what these comets are made of. So in 2014, Rosetta and Philae got there. It took 10 years to get to this comet after we launched it. Philae was designed to go down to the surface, and you can see these series of images of Philae descending down to the surface with its 3 legs taken 5 minutes apart. It was meant to touch down, fire sort of itself down into the surface to secure it, stay there and make its measurements. And it didn't. It bounced. It bounced off the surface. So you can see the before and after image here, where there's no depressions in the surface, and here there's 3. The legs touch the surface, but the lander isn't there. It actually bounced off to the side. The comet was much, much harder, we thought, on the surface. That solid water ice, again, that we just talked about in Pluto. But the lander did touch down, not where it was meant to. This was one of the images we saw. And 2 years later, they actually managed from Rosetta orbiting to find where it had landed. And if you zoom in right on this image, it's buried down in this crevasse down here. It needed solar power to charge its batteries. And down there doesn't seem to be particularly sunny. So instead of lasting for an extended period of time for the mission, it lasted a mere number of hours. In that time, it still made its direct measurements, though, of what these comets are made of. It knew about really hard water ice because it bounced. It discovered molecules containing carbon and hydrogen. And it discovered organic molecules. Those together are the building blocks of life. So if we're starting to say, how did life form here on Earth? We now know these comets that go flying around our solar system have the building blocks of life on board. Again, we only discovered this back in 2014. A big piece of the puzzle if we're trying to go, where did we come from and how did we get here? Now, I could talk for probably another 4 hours about all of the missions in the solar system right now. I could talk about Cassini, that plunged down into the outer parts of Saturn at the end of its life in 2017. This is one of the last images it ever took of the rings of Saturn. I could talk about the Mars rovers and their selfie shots on Mars. We have Curiosity and Perseverance there at the moment. We've had Spirit and Opportunity before and others. We now have a helicopter called Ingenuity on the surface of Mars that is still flying all over the place, far longer than we expected. I could talk about the Juno mission to Jupiter. This is a view that was taken a couple of years ago now of the southern pole of Jupiter. We had no idea what that looked like. And we can see these huge cyclones that are 600 kilometers across, just like the big red spot, all of those storms on Jupiter. We now can see at the southern hemisphere and the northern hemisphere of Jupiter that we never knew about before. We could also talk about the sun, the star nearest to us with the Parker Solar Probe, flying closer and closer into the sun over the next few years. The mission description is the first mission to ever touch the sun, the outer parts of the solar atmosphere, and directly measure its composition. So I could talk about all of those, but I'm not going to, because we're going to talk about some of the broader astronomy things. That's our nearest neighborhood, though. It's exciting places. We're doing exciting science. Astronomers don't just look in our own solar system now. We look further afield. And today, as of earlier today, we now know not about the 8 planets in our solar system, but 4,935 other planets that aren't orbiting around our sun, so-called exoplanets. This is one of the fastest growing areas of astronomy. And we have a bunch of different ways to measure them. Most of them were discovered by the transit method from what was called the Kepler mission. And this was launched back in 2009 and worked for a period of about 5 years, staring at patches of the sky, looking for brightness changes, periodic brightness changes that are a signature that there's a planet in orbit around that star. We now know they exist. It was exciting when we discovered the first one. It was exciting when we discovered the first 100. Now we've discovered the first 5,000. It's sort of more like stamp collecting. Some people love it. It's like, and we've discovered another planet, great. So what we're now trying to do is understand what we'd say the demographics of exoplanets are. Not just they exist, but are they rocky? Are they gaseous? Is there an Earth 2.0 out there somewhere? We're trying to build up that bigger picture. We are also able to do some really fantastic things of direct imaging these exoplanets. So right at the center of this image, where the yellow star is a star if we look at it in the sky. We block that out with what's called a coronagraph. And you can see 1, 2, 3, 4 dots moving around it. This video is taken over the series of about 7 years at the Keck Observatory. And what you are seeing is planets orbiting around another star. This is a specific star that astronomers know about. It's called HR 8799. We really suck at naming things. It's a catalog number. But this is one of the most famous planets that we have in exoplanets because we can directly image these planets. Now, these are not planets like Earth. These are planets from when our solar system was just forming. So they're sort of hot blobs of gas and rock. They're not suitable for life. But we are starting to get to the point where we can directly image these planets around other stars. And that's incredibly exciting. Everything I've sort of talked about at this point is all about being sort of observed and studied using light. And a huge, huge discovery that's going to completely change astronomy in the next couple of decades is gravitational waves. Now, how many of you have heard of gravitational waves? How many of you understand gravitational waves? Sort of, okay. So the way I like to think of this is not gravitational waves, but the mysterious world of gravitational waves, because to understand gravitational waves, you need to forget everything you know about life on Earth, because these are nothing like everyday life we experience. What you can see in this image is sort of a grid that's being distorted. And I want you to keep that in mind. Imagine instead of the three-dimensional world we live in, you're a tiny little bug that can only exist on the surface of this desk, or on a piece of paper, or on a sheet of rubber, a 2D flat surface. So here we go. Here's our bug on that surface. And that bug can only ever stay on that surface. It can't come off the sheet. It can only ever stay on that sheet. And what I say is, everything that has mass can distort that sheet that that bug is on. So imagine that bug is on a rubber sheet, and I put mass on there. I put a bowling ball on there. What's it going to do to that rubber sheet? It's going to distort it, exactly, okay? The bug is still on the rubber sheet. So if it wants to go from one side to the other, it has to go down that dip and back up. And that is the entire premise of Albert Einstein's theory of general relativity and space-time and all kind of things. And if you would like a graduate course in it, come to Notre Dame. But I don't think we're going to go into that level of detail tonight. But that's the kind of concept, okay? You have that sheet, which is the universe that that bug lives in, and we can distort the shape of it, okay? So coming back to this image, you can see that sheet is being distorted by our sun and also a little bit by our planet Earth. The amount of mass governs how distorted the sheet gets. Now we know Earth orbits around the sun. So that means this sort of dip here is going to move as the Earth goes around the sun. So if you have two things in orbit around each other, they are continuously changing and distorting that sheet. Okay? And in this video, as they get closer and closer and closer, the ripples they create, the ripples in space-time as we call them, travel out closer and closer together. So I'm just going to go back and play that again. If you watch, these things orbit around each other just like the Earth around the sun. The ripples are quite spaced out. These things get closer together. The ripples get faster and they get bigger. So what gravitational waves can be used for, if we see these changes, if we are able to measure them, and we see this, what we'd say the frequency, how quickly those peaks come, those ripples closer together, increase in the amplitude, the size of those ripples gets bigger, says we have two things merging together in the universe. That's the high level of the idea of what we're talking about. So if we can measure these gravitational waves and see this pattern, we know we have two things merging together. That's the idea. So we can do that by shining laser beams 90 degrees to each other and measuring how they interfere together. It allows us to measure those ripples. That's the high level picture. And LIGO, which you can see a picture of here, does that. So it has those 90-degree beams. We're shining laser beams down each of these. Each arm is about 4 kilometers long at ultra high vacuum with basically no air in there at all. And we're trying to measure a change that is a tiny, tiny, tiny fraction the width of a hydrogen atom in the length of that arm. So it's taken a while for us to have the technology to be able to do that. You can imagine a truck driving down the road next to this is going to make everything move, and you're going to distort your images. A good way to think about this is imagine we packed this room full of people and everyone was talking to the person next to them, and I want to hear the conversation of the person at the back. Okay? It's incredibly hard for me to hear it through all of the noise. But if we could measure all of the other noise by putting microphones next to everybody, I'd be able to subtract all of the other conversations and I'd be able to hear the conversations at the back. So that's kind of the idea of what LIGO is trying to measure. To give you a sense of scale, the width of a tiny hydrogen atom is very, very hard to sort of put in context of how small this is they're trying to measure. If you take the distance to the nearest star, which is about 4 light years away, and you change the distance by the width of a human hair, that's the difference in scale we're trying to measure here with these instruments. It's incredibly, incredibly challenging. The way they bounce these laser beams back is they have optics that are very carefully strung to make sure they don't vibrate and move around. But it was exciting when, in 2015, LIGO detected the first signature of gravitational waves. And they do this by having 2 sites. There's one up in Washington State at Hanford, and there's another one down in Livingston, down in Louisiana. Because if they both see the same signal, it means it's coming from space. It's not a truck on the road. So by having both of them, you can really be like, yes, there is an actual signature there. So if you remember, those gravitation, those objects merging together and those ripples, what they've done is sort of take the signal they detected and put it into audio so we can hear it. So you can hear it going up in pitch and getting louder. So it starts very deep down and gets higher up. That's literally the signal they have. And from that, they can tell you that it's 2 black holes that were merging a billion years ago on the other side of the universe from that signature. You might not believe me, but the science community did. And this is why the people involved with this got the Nobel Prize in Physics in 2017. But before this detection, we had only ever studied the universe using light. This is a whole different way to study the universe. It's like having a different sense. We could only see things before. It's now we can almost like touch things. It gives us a different sense to study, way to study the universe out there. And that's why it's incredibly powerful. Since then, there's been more of these detectors come online. The Virgo collaboration in in Italy. We've got collaborators out in Japan doing this kind of things with these new gravitational wave observatories. And in 2017, Virgo and the LIGO positions detected, and there's a whole story behind this. They didn't think they detected something, and they decided they did detect something because they had a glitch in their data because there was a train at one of the sites and all kinds of fun games. But 2017, 17th of August, they detected the merger of 2 neutron stars, remnants of stars. And for the first time, they didn't just detect the gravitational waves. We saw light as well from that merger. The important thing about neutron stars merging is it's a place where we can create some of the elements we know exist in the universe. This is Notre Dame. We like gold. We have a golden dome. We didn't know how the universe could create gold before this event. We're now like, aha, we have a physical process that allows us to create those heavier elements. So this detection, and this was the paper came out of it, they detected gravitational waves, gamma rays, X-rays, and they did lots of other measurements. They basically said, dear astronomy community, we've got gravitational waves. Please go point all of your telescopes over here and tell us what you can see. So the community did, and we now have all of these companions. So we can now make the heavier elements in the universe that we didn't know for sure. We had ideas. We've now detected those for the first time. So gravitational waves is going to be a big, big part moving forward in telling us, allowing us to see the universe in a different way. The last discovery I'm going to sort of briefly touch on of the last decade is one that called the world by storm. And it was the first ever image of a black hole. So this was announced in April 2019. And this is the black hole at the center of the galaxy Messier 87. It's a supermassive black hole. And what you're seeing around it is effectively the material that gets superheated, very hot, spiraling in. So this has X-rays and things like that. The Event Horizon Telescope that took this data is a combination of many telescopes working together, combining their data in interferometry to be able to make this image. And they're currently trying to upgrade the system. It's an international collaboration. International travel has been a little challenging since 2019, so they're still trying to do that upgrade. But the idea here is to be able to really zoom in and study some of these things in incredible resolution, incredible detail that we've never been able to do before. So this was a stunning image that they managed to create, and here's hoping we get more in the next few years. So that's what we sort of know about right now. The question is, well, what don't we know about? And often as a scientist, you know, from an outside, you might be like, oh, there's, you know, a few things we don't know. Scientists in everyday life tend to have all of these other ideas with many different things that we don't actually really know about. So there's many questions we still need to study. In astronomy, what we do every 10 years is go through the process of asking all of the astronomy researchers what are the most important things we should focus our scientific resources on answering and understanding. And this started back in 1964. And the most recent one, this is the US-based perspective on this. There was one released last year called Pathways to Discovery in Astronomy and Astrophysics for the 2020s. And this is what we call the Astronomy Decadal Survey. So the end of last year when this was released, everyone was kind of going, what's it going to be in there? We don't know what's going to be there. Is my research going to be in there? Should I be doing something else? Where's the money going to go? So this is, we'll talk about basically this one for the rest of the talk. But I just want to say, you know, the US perspective is not the only one here. European astronomy has a strategic plan about where they should go. And NASA has its own idea this was released, I think, in 2014 as a roadmap. What should NASA do for the next 3 decades? Where should they spend their money? What technology should they invest in? So there's always this thinking about what do we need to invest in now for future scientific needs, because it takes time to develop the technologies. So Thursday, November 4th, 2021, everybody in astronomy tuned in at 11 a.m. when this report was released. The entire astronomy community in the world managed to denial of service the National Academies of Science servers as we all tried to get our hands on this report simultaneously. And social media went crazy going, do you have a copy of the report? Can you email it to me? Because no one could get their hands on it. It's a total of 589 pages covering everything from what are the important research questions? What are the telescopes and observatories we should build? But also, importantly, the state of the field. Are we supporting scientists in their research? How are we making science more equitable? Are we addressing science to make it representative of the population as a whole? You know, the scientific community should represent the US community as a whole. Are we there yet? Not really. We need to improve minorities, women in STEM as a challenge. So how are we doing that? So they tackled all of this. And I want to briefly read you a section of the summary, because I think it puts into perspective quite nicely of where we are. So it said, we live in an extraordinary period of discovery in astronomy and astrophysics. 6 Nobel Prizes have been awarded over the past decade alone for discoveries based on astronomical data in dark energy, gravitational waves, neutrino oscillations, the discovery of exoplanets, cosmology, and supermassive black holes. Many of the ambitious visions of the previous decadal survey are being fulfilled, but momentum has only grown. We stand on the threshold of new endeavors that will transform not only our understanding of the universe and the processes and physical paradigms that govern it, but also humanity's place in it. So it's kind of a broad vision of what we've been doing, but where we should go. So how did they come up with the report? Well, basically, you have a panel of experts that normally meet in person and got very familiar with Zoom meetings, as we've all been doing over the past couple of years. And they had the job of sifting through 573 white papers that the community submitted to them about science, 294 about the state of the field, and figuring out, with all of this input, what is the best direction for astronomy. So all of this basically funnels into that final report process. It's not just the people on the panel. We write, as a community, these white papers, and you try to get people to buy into it. So I was on a few of these. I wrote one of these, and I was soliciting people, being like, my idea is great. Will you sign on to my proposal? And mine's the way we should go. And it's trying to get a consensus among the community about ways to go. So there was 3 main themes that came out of the most recent survey. And it really was to try, the vision is sort of to have some of the most exciting and new discoveries that we can in astronomy and astrophysics, and put our place in the universe into better context. The first theme was worlds and suns in context. And the high-level description was pathways to habitable worlds. We are looking for planets like Earth around sun-like stars, Earth 2.0. That is what they say is one of the key, most important things for astronomy in the next decade that we should be prioritizing. If you want to summarize it, is there life out there? The second one was new messengers and new physics, and that's a bit of a weird one to kind of say, but the universe is continuously changing. We saw those merging stars and gravitational waves. We know we have flares that come from stars and black holes. And what they were saying is we should be combining all of those different types of observations to build a better picture of how the universe changes over time. It's what we call time domain astronomy. So that's what we're trying to look at, looking at black holes, neutron stars, gravitational waves. The third idea is what they called cosmic ecosystems. How do we go from the Big Bang to form the galaxies, to form the stars, to form the planets? How do we build that broad ecosystem? How do they all feed together in an ecosystem? You have different players that all sort of funnel into each other. How do we build that broad context of how we got here in the universe? So those were the big 3 ideas, tackling questions like, are we alone? And the joke in terms of astronomy is we use the word dark matter and dark energy. You can tell me what the word dark means in that context. Answers on a postcard, because we still don't really know what dark matter and dark energy are. We see their effects, but we don't actually know what they really are. So the big questions we're trying to answer: are we alone? Looking at exoplanets, the search for life. How did we get here? Stars, the elements in the galaxies that we see, and how does the universe work? The extremes of nature. So we sort of got plenty to ponder. So that's the big question. Those are the big questions. How do we answer those? Well, we need a set of tools.
10, 9, 8, 7, 6, 5, 4, 3, 2, unité, top.
And we have engine start. And liftoff.
Décollage.
Decollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe.
So astronomers got a Christmas present this last year on the 25th of December. James Webb launched from French Guiana. I was actually in California at the time, and I was up. It was like Christmas morning as a kid again. I was up at stupid o'clock to be able to watch this thing go up. But I think astronomers were very happy to be up early that day. So James Webb is billed as the successor to the very famous Hubble Space Telescope. It's going to be able to see things 100 times fainter than Hubble. The difference being that it's going to not be looking in the ultraviolet and visible light that Hubble sees, but in the longer, the red light through to the infrared that is too long a wavelength for our eyes to see. What that's going to allow us to do, though, is look at galaxies even further away than ones that Hubble's been able to see. So we're going to stare even further back to the beginnings of the universe, studying those galaxies and how we got here. How did we go from the Big Bang to those first galaxies? Cosmic origins is the way it's described. Now, James Webb comprises 18 individual mirror segments that they have to piece together to be able to do that science. And they have to get this very cold and very precisely aligned. This is about 6.5 meters across. So to do that, they put it behind a huge sun shield. And there are a series of instruments that are going to allow us to make these measurements. There's 4 NIRCam, which is an imager. We'll see some pictures from that in a moment. NIRSpec, which is a spectrograph that looks at the colors of the light coming from the universe. And we have MIRI, which is a camera and a spectrograph. And we have NIRISS, which is a slitless infrared spectrograph. So we're looking at both images and the colors of the light. Now, James, every time I've given this sort of talk, I always have to update it with James Webb will launch. And it was originally planned to launch in 2007, then 2014, then 2017, and eventually it was 2021. And it originally had a budget of $500 million, and it's now cost $9.8 billion. So it's a little different, but it's because we're building the technology that we've never done before. And it's still so important that astronomers lobby Congress to get the funding to do it, because it's so important in given the context of where we are in the universe. The timeline for James Webb, for those of you who haven't necessarily maybe been following it, is it launched back on Christmas Day. And along the top here, you could see basically weeks, so 4 weeks, 8 weeks, 12 weeks, and 16 weeks of where the telescope is in its commissioning. It has to fold up to fit in the rocket the Ariane 5 at launch on. They have to unfold the sun shield. They have to open the mirrors and everything else. And everyone in astronomy sort of was on edge for the first month or so while they did these deploys. There were many things that could go wrong. Everything went perfectly. So everyone's now a little more calmed and relaxed about it, rather than having a very expensive $9.8 billion paperweight that can't do science. So we're very happy that it's actually deployed. And a couple of weeks ago, they actually released the first light images from James Webb. And I want to put these in context, because I work in optics. To me, this makes complete sense. But talking to someone else, they're like, what am I looking at in these images? So that mirror has 18 segments. And when they launched it, you effectively didn't have one big mirror. You had 18 little mirrors. So each point of light is from looking at a star on one of those mirrors. This is not how we're going to do science. This is starting to figure out which dot of light is which mirror, so you can move them into the position to get that nice mirror shape. They also were able to take a selfie. This is the equivalent of the Mars rover selfie. They were able to take a picture of all of their mirrors from one of the instruments. This is from NIRCam. And since they started this is the initial image. If you imagine that the light from the telescope hits the mirror, it goes to the secondary mirror and then goes down to the instruments down here. They're constantly tweaking both each segment here, but they can also tweak the secondary mirror, move them in parallel to improve the image quality. So they started here, and they've now got here. So an iterative process to move this together. And they actually built a small scale model of James Webb in the lab at Johns Hopkins to figure out how to do this process in space. So we're getting better. And then a few days ago, they actually moved all of those points of light together onto a single image. Now, this looks much better. It's still not great. It's still not perfect. And they've still got a long way to go. They've still got about another 2 months, 3 months worth of commissioning to go. But eventually, we'll start getting those stunning images like we get from Hubble and being able to do it. So looking ahead, James Webb is not the only thing that's out there. It's the exciting, shiny new thing right now, but there's still a lot of other stuff going on. These are just some of the space missions that are existing and coming up over the next few years. IXPE was another NASA mission that launched in December 2021 last year. We have a sample return coming back from an asteroid, from the asteroid Bennu with the OSIRIS-REx mission that's coming back September next year. We can get a sample of it. study the material that those asteroids are made from. We also have things going on the ground. That's what I do at my day job, is working on ground-based telescopes. That's easy for us because we're like, well, there's an old instrument, I'm going to take it away, and I'm going to put a shiny new one on with the new technology. It's a lot easier than doing that than in space. So we're constantly upgrading those telescopes. We're also going to have the Vera Rubin Observatory coming online next year, which is designed to look for changes in the stars and things in the universe. So those transient, those changing effects is what it's designed to do. And then we've got radio telescopes and the extremely large telescopes. Again, we're not very original with our naming, coming online at the end of the decade. And this is a picture of one of them, which is the giant Magellan telescope. It has 7 8.4 meter mirrors combined together to make 25.4 meter across diameter mirror. And this is just one of them that's going to be coming online. So we have all of these tools that are designed to answer those questions. This is a picture from last year. They're actually building this down in Chile in the Atacama Desert. And this doesn't really, you can see vehicles and things. These are those 7 mirrors mapped out on the ground, and you can see people there for a sense of scale. So this thing is going to be a monster. And I know the people who work on it, and they have a lot of technical challenges to work through before we're going to get some nice images, but we'll get there in the end. So in the last couple of minutes, what about looking further afield? Well, we're not quite going as far as too far into the future in technological challenges, but particularly in space, these science missions take a very long time to mature. They can take 20 to 30 years from an initial idea to become a reality. But the challenge with that is one big constraint. That is always money. It costs money to pay people. And most of these things are funded from federal dollars, from the federal government. So if you like science, I encourage you to go lobby your House representatives and your senators to be like, give science more money. We'd love to do more if you gave us more money. But it means that we have to prioritize, and that is what the Decadal Survey is partly about. The big thing in terms of the longer term view that the Decadal Survey said is James Webb had a huge cost overrun and was incredibly delayed because the technology just wasn't there. And they've said that we should improve that technological maturation, is what they say, taking maybe a decade to build the technology we need before committing to a mission. So that's one of the key things they said. But they came back with one big idea that we should push forward for, launching in about 2040. And it is a 6-meter aperture telescope in space, but it's not infrared like James Webb. It's optical and ultraviolet like Hubble. And the goal of that mission is to be able to take direct images of planets like Earth around sun-like stars. So not those hot, newly formed planets like we saw back in that movie. Solar systems that look just like our own. And we should be able to look for signatures of life. So by 2045, hopefully, that's hope for your question, we'll be able to answer. And that was kind of the long-term view of where astronomy is being pushed to go for the next decade or so. So I'm going to stop there. Thank you all very much for coming, and I'm happy to take questions. For people online, if you have questions, feel free to put them in the Q&A. Any questions in the audience? Laszlo.
So if James Webb,
Mm-hmm. Exactly. So the question was, if James Webb can detect infrared light, it can detect life and things as well. It can, and it's going to do spectroscopy looking on certain exoplanets for potential biosignatures. But that's not going to be around sun-like stars. It's going to be lower mass stars typically where we might be looking for these kind of things. So it will start to give us more information, but it's not going to get us to an Earth definitive answers of life elsewhere in the universe. It might give us some indicative information, but it's not going to have, it isn't big enough to necessarily and sensitive enough to be able to make those measurements precisely yet. We just don't have the technology. And particularly the instruments were actually ready for James Webb. It's the rest of the telescope that took time. And once an instrument is finished, you don't go back and touch it once it's ready for space. So a lot of the instruments have been sat around for many years now. And our technology has moved along significantly. And we're like, but we want to go and make it better. And NASA says that costs more money. You can't do it. So that's just the reality of space missions and certifications. So, yeah. Mm-hmm. Good question. So the question was, several times I've mentioned that the federal government funds a lot of this. What about the private sector getting involved in this? So the private sector tends not to be so interested in the fundamentals of studying the universe. But what the private sector is able to bring is things like reduced launch costs. And for a lot of these missions, launch costs can be hundreds of millions of dollars to launch these things. So if you can reduce that by a factor of 2, by having competition and innovation in the private sector, you can, if you have that fixed pot of money, you can make it go further and do more science. Now, there is some technology innovation and things that really have pushed the boundaries. If you're looking at detectors and cameras, for example, we all have cell phone cameras and digital cameras everywhere, and we've improved that technology. So some of that innovation can absolutely be used. The challenge is sometimes there's not many commercial applications of sort of infrared detectors. There are many if you're looking at things like heat signatures from missiles, but not necessarily from a everyday perspective that will help bring some of those costs down. Sometimes you can get it, sometimes there are useful things, but it's sort of specific areas rather than the general things. A lot of these are one-off builds where we try to combine these things together, but great question. Do we have any online? Any other questions? Yes.
Water, ice, and Pluto.
That is a good question. I can't remember the exact temperatures out there, but you're going to be getting probably minus 200 Celsius to minus 300 and odd Fahrenheit out at the edges of the solar system, because there's no heat from the sun really to warm things up. I mean, in lab conditions here, we can get very cold. We can do it, but typically to do that, we do a lot in vacuum. And if there's an atmosphere, it just makes it very hard to do it because we conduct the heat away. So we can do some of those tests and different things. I think it's coming back to the Pluto idea, it was, why do you have the blocks of ice? And then why do you have the nitrogen ice looking like this flat, smooth surface next to it? So it wasn't, we didn't expect it to be, have water ice out there, but seeing those very strong contrasts and how did we get that structure is one of the kind of big questions that came from that. So, yep. There are exoplanets around the nearest star, so around Proxima Centauri, so about 4 light years away. Coming back to the Parker Solar Probe, that's going to be the fastest man-made spacecraft in about 2025, and it's going 450,000 miles per hour, which is 0.06% the speed of light. So it would take you 800 years to get there with the fastest man-made spacecraft. So we're still a little away from being able to go and say hello to aliens. So, but that's the nearest one that is to us right now. So, yep.
Can you say a little bit about the process to get James Webb fully operational with that 2-month period of like where they've got all the images aligned? What is there?
A lot of pushing buttons on computers. So every basically mirror surface on the telescope is adjustable. And what they're doing is what they call phasing the mirrors. Many of the big telescopes on the ground have segmented mirrors, just like James Webb has. And sort of, you can imagine if you have one mirror here and you have one mirror stepped back and you're dealing with light, that's never a good thing. So what you need to do is phase them together so you have a nice continuous surface. So they've adjusted effectively the primary and the secondary into the correct position now. And now they've got to tweak each of these segments to phase them together properly. And that just takes time and patience, because you can't just be like, let me go take another measurement with a different tool. You only have the tools you have. So they have a process. They just have to go through that process because, again, they launched everything on a rocket that shook everything pretty vigorously. So we're all very happy it survived. They just have to now go through that process. So, Dave, I'll take. I'm sure they have, but they haven't told anybody. You want it to be a surprise, right? It's like you don't want to know what your birthday presents are. You want to be surprised by them. So. Awesome. I'll be at the front of you. Do you have any other questions? Yep. Yes, it does. No, it's 1.5 million kilometers. So it's seconds, if that. It's pretty close. So a bit further than the moon. And the moon's about a light second. So, Laszlo, one final question. Money, probably. Money. But so LIGO, the question was why are there only 2 LIGOs? I assume it was a cost thing because these things are expensive. But now we have all of these all over the world. And so we have more data points to be able to kind of piece those together. There's also stuff to do with triangulation about where you position them. And I don't know if given that you have one at the northwest corner of the US and basically the southeast, that might be the best coverage you could get in the US. And it maybe didn't bring any benefit from doing triangulation. So we'll stop there. I'll be down at the front if you have questions. We'll be back in 2 weeks. We're not talking astronomy. And we have a visiting professor here at Notre Dame who's going to be talking about how do physicists come up with different theories and sort of our most beautiful theory so far. So how does sort of science change? How do we come up with our theories? And how do they adapt and evolve? So it's back in 2 weeks' time on the 15th. So thank you all for coming and hopefully see you then.